When water moves, we can often see patterns. Here, at the Victoria Falls, it's quite a complicated pattern. But for this whirlpool, it's a little simpler. The pattern is caused by particles flowing as time passes. Here, the particles are water molecules, but they don't have to be. This galaxy appears to be flowing in a spiral around its centre. Real flows like this are quite difficult to analyse mathematically. Here at the University of Exeter, Dr. David Buckingham and his colleagues have some apparatus for measuring the flow of fluid under controlled conditions. In this demonstration, we can see a flow which is radially outward from a central source. The same equipment can be adapted to show the flow past a short obstruction. The die shows the flow starting as a parallel stream, but then bending past the perspex plate. Near the middle of the plate, the curve looks rather like a hyperbola. This flow is still quite complicated, but there are some flows which we can analyse mathematically. In this experiment, the fluid moves in circular paths, as we can see by carefully dropping some dye onto the surface. And here, we're rotating the fluid round a vortex, rather like in a bathtub. If we add some fine aluminium powder to track the flow, we can see interesting spiral patterns. Let's see how we can model this flow. The pattern is a spiral which moves towards the origin, and the further away a point is, the faster it flows. To see what happens to the fluid at a particular point, we can imagine its velocity. A short time later, it will have moved to a new point, where it has a new velocity, and so on. This flow goes around the origin. Once again, at each point there's a velocity which determines how the fluid is about to move. The path through any given point is called a flow line. With this flow, the fluid seems to flow away from the origin. The flow lines are quite complicated, but as always, there's a velocity at each point. Well, that's just a few of the patterns we'll be looking at, but they all arise in a very specific way. They're called linear flows. How do we get them? Well, at each point, we associate a velocity. So velocity is a function of position, x and y. If the function happens to be linear, it's given by multiplying x and y by a fixed matrix. It's linear flows we're going to concentrate on in this program because we can use linear algebra to analyse them. What can we say about such flows in general? One thing you probably spotted on the animation. The origin never moves. According to this formula, the velocity at x equals 0, y equals 0 is 0. And no velocity means no movement. Well, that's all very well, but what happens to the other points? Peter?
Well, it turns out the shape of flow you get will be one of these. But the direction of all the arrows might be reversed, so that here the flow might go clockwise rather than anti-clockwise. But the general pattern will still look like one of these. Of course, we've done our best to make these look as simple as possible. For instance, whenever the flow is a straight line, we've used that line as an axis. And we've chosen our scales carefully too. If you don't do that, then the shape may appear slightly different. In this case, both the x-axis and the y-axis are flow lines. But if we change our coordinate system, change our basis if you like, we can deform the model. The general shape's the same, into the origin along here, and out along here, and past the origin along these hyperbolas. Here's another example. The flows are circles, but by a suitable rescaling of the axes, we can get ellipses. And if we hadn't chosen the direction of the axes carefully, we might have found that the ellipses are rotated, like this. And we can even reflect our axes to change a lovely flow like this into one like this. So our claim is that any linear flow looks like one of these, possibly with the arrows reversed, provided we're careful about choice of axes and scales. And all that amounts to is a good choice of basis.
Well, why should that be? And how can we find the shape of the flow? One way is to find each flow line explicitly. Now, a flow line is a curve. Any curve can be described parametrically. As time passes, a given point will flow along the curve. As it does so, its coordinates are functions of time, and the curve is described parametrically by x equals f of t, y equals g of t. Actually, for a linear flow, both the coordinate functions satisfy the same differential equation, and here it is. The trace of the matrix A is just A plus D, and the determinant is A times D minus B times C. By solving this differential equation and using a bit of algebra, you can find the coordinate functions f and g, but it's quite a lot of work. The first step is to write down the auxiliary equation and solve that. We're not going to pursue this because we want to get a feel for what the flow looks like rather than find exact equations for all the flow lines. The fact is that we can use this equation to find the shape very quickly. You may have spotted that this equation is also the equation from which we find the eigenvalues of the matrix A. And since the flow is defined by A, well, perhaps it's not so surprising that its shape depends on algebraic properties of A, such as eigenvalues and eigenvectors. We're going to investigate this relationship between the shape of the flow and eigenvalues, and we'll see that we can virtually read off the shape once we've found the eigenvalues. Well, what possibilities can arise? Well, the first basic question to ask of any matrix is it singular? In other words, is its determinant 0? If it is, then the eigenvalue equation has this simple form. And we can see that lambda equals 0 has to be one solution. In fact, if trace A is also 0, then we have a repeated eigenvalue 0. One obvious way this can happen is to start with a zero matrix. At each point xy, this assigns the velocity 0. Well, the result is that nothing ever moves, and this is definitely the most boring of the linear flows. But there are other matrices for which both determinant and trace are 0. The simplest is this matrix, where there's a single entry in the top right.
Taking B as 1, we get the matrix 0, 1, 0, 0. The velocity at any point on the x-axis is 0. So points there don't move, and the x-axis forms a barrier. For a point on the y-axis, the velocity is parallel to the x-axis and depends on its distance from that axis. So when y is negative, it points the other way. For this point in the first quadrant, the velocity is again horizontal, as it is for this point in the third quadrant. Filling in the flow picture gives this pattern.
Okay, but what if A is still singular, but its trace is non-zero? Well, lambda equals 0 is still a solution of the eigenvalue equation, but this time lambda equals trace A is a different solution. The simplest matrix which behaves like this is lambda 0, 0, 0. We're going to look at the case where lambda equals 1.
For points on the x-axis, the flow is radially outwards. For points on the y-axis, there is no movement. For this point, in the first quadrant, the flow is horizontal, as it is for this point. And filling in the flow picture, we get this. Notice that the eigenvectors, here both the axes, correspond to lines on which the flow is 0 or radial. We call these barrier lines. Well, that's all that can happen if the matrix A is singular. If both eigenvalues are 0, we either get no flow at all, or this peculiar shear-like flow. And if one of the eigenvalues is non-zero, then what we get depends on the sign of the eigenvalue. Now, how does that work? Starting with no flow, both eigenvalues 0, we let one eigenvalue increase gradually. The flow is away from the y-axis and parallel to the x-axis. As lambda increases, the flow looks the same, but simply moves faster. Now let's decrease lambda. Back through 0, where there's no flow, and let it become negative. A similar pattern emerges, but this time the flow is towards the y-axis. The more negative lambda becomes, the faster the flow.
Well, if the matrix A is singular, there are no other combinations of eigenvalues. But what happens if A is non-singular? Well, now the story becomes more interesting. You see, we now have a general quadratic equation here for the eigenvalues, and so we can find ourselves in one of three possible situations. Either the roots are real and unequal, or they're complex, and in fact complex conjugates, or they're real and equal. We'll go through each of these in turn, again taking the simplest possible matrices as typical examples. In the first case, the eigenvalues are real and unequal. The simplest example of this behaviour is just a matrix where the eigenvalues are on the diagonal, like this. In this situation, there are always two linearly independent eigenvectors, and in our case they're the x and y axes. The shape of the flow we get depends on the signs of the eigenvalues.
Here, at points on the x-axis, the flow is radially outwards. So this is a barrier line. Here, on the y-axis, it's also radially outwards, giving another barrier. At this point, in the first quadrant, it's outwards but upwards. And here in the third quadrant, it's sloping downwards. Filling in the picture gives this outwards flow. It's called a source. And what happens if we change the signs of both of the eigenvalues from positive to negative? Well, the flow is similar, but inwards. It's called a sink. But if we change the sign of only one eigenvalue, the flow changes completely. The x-axis is still a barrier line flowing outwards, while the y-axis is a barrier line flowing inwards. Here, in the first quadrant, we flow down to the right. And here, we flow up to the left. So filling in the picture gives this. All the flow lines are hyperbolas. So, if the eigenvalues turn out to be real and unequal, we're going to get a flow which looks something like one of these. And as we've seen, it's the sign of the eigenvalues which tells us which one it actually is.
Right, now for the second possibility. What happens if this equation has no real roots? In other words, the eigenvalues are complex. What sort of flows do we get? Well, the simplest such matrix is A minus B, B, A. and the eigenvalues are just the complex conjugates A plus or minus IB. This matrix is not unlike a rotation matrix. Just imagine A as cos theta and B as sine theta. This provides a valuable clue as to what to expect. We'll look at the simplest case, where A and B are both equal to 1.
This time, there are no real eigenvalues and no eigenvectors, and so there are also no barrier lines. On the x-axis, the flow is either upwards, like this, or downwards, like this. And similarly, on the y-axis, it's to the left or the right. At this point, it's turned upwards, like this. And here it goes downwards. So what's the flow? Well, filling in the flow picture, we get this outward spiral. It's outwards because the real part of the eigenvalue is positive. If the real part is 0, we get concentric circles. And when it's negative, the flow spirals inwards. Well, that's finally dealt with two of the possibilities when A is non-singular. We know what the flow looks like if the eigenvalues are real but unequal, or if they're both complex. So what's left?
Well, what remains is the possibility that the eigenvalues of A are real and equal. This quadratic has repeated roots. Now, as usual, the shape of the flow will depend on the sign of the eigenvalue. But there's something else. You might remember that with repeated eigenvalues, we may be able to find two linearly independent eigenvectors. Or we may only be able to find one. Now, this has a crucial bearing on the shape of the flow. The simplest matrix with two linearly independent eigenvectors is this one. So what does the flow look like?
Here, we've chosen the eigenvalue lambda to be 2. On the x-axis, the flow is outwards, as it is on the y-axis. But in fact, the flow at any point is radially outwards, and the flow looks like this. It's another source. Here, all radial lines are barriers, since every vector is an eigenvector. And when the eigenvalue is negative, we just get an inward flow, a sink.
Well, we've got a repeated eigenvalue, and we've just dealt with the case where you can find two linearly independent eigenvectors. The simplest example where there's only one is this matrix, lambda 1, 0, lambda. So now what's the flow going to look like?
Here, we've chosen lambda equals 1, and the only eigenvectors are points on the x-axis, where the flow is outwards, along the barrier line. At points on the y-axis, the flow is like this. And for a point in the first quadrant, like this. And in the second quadrant, it's like this. What we have is a bit more complicated than usual. Can you guess what the flow picture looks like? Well, since the eigenvectors only give one barrier line, the x-axis, it has to look like this, an odd outwards flow. And if the eigenvalue had been negative, it would have been inwards, like this. So, what have we discovered? Well, we've investigated the kinds of flow which arise from all the different algebraic possibilities for the matrix A, using the simplest choice of matrices. So in fact, what we've done is completely catalogue the shapes you can get from a linear flow. So let's summarize them. If A is singular, then at least one of the eigenvalues is 0. If both are, it's either no flow or this flow. And if only one eigenvalue is 0, then we get one of these shapes. And as usual, the direction of the flow depends on the sign of the eigenvalue. If A is non-singular, we have the three possible cases. First, the eigenvalues could be real and unequal. And we get pictures like these, according to the signs of the eigenvalues. Or if the eigenvalues are complex, we just get one of these. And which one depends on the sign of the real part of the eigenvalue. And finally, if the eigenvalues are real and equal, we get one of these. It's one of these two if there are two linearly independent eigenvectors, and one of these if there's only one linearly independent eigenvector. Well, that's the lot. And so any other linear flow looks like one of these, because of course any matrix can be reduced to one of our simple examples by using a suitable change of basis.
Well, to see how all this works, let's take a particular example. Which pattern is this flow going to have? Here's A with trace 2 plus minus 4. Well, that's just minus 2. And the determinant of A is 2 times minus 4 minus 3 times minus 3. And that's just 1. So the eigenvalue equation is lambda squared plus 2 lambda plus 1 equals 0. And this has equal real roots of minus 1. So our flow is one of these two general shapes. The flow must be inwards because lambda is negative. To find out which type, we'll search for linearly independent eigenvectors. Because this has 2, while this has only 1. To find the eigenvectors, we solve this vector equation, which gives this pair of linear equations. In fact, both these equations reduce to x equals y, and so all the eigenvectors must lie in this one line. There's only one linearly independent eigenvector, which means the flow's got to be like this, except that the barrier line is deformed to x equals y. So it's like this, or possibly its reflection in the barrier line. To find which it is, all we have to do is plot the velocity at one point. Here it is, and so here's the final flow picture.